In quantum entanglement, the vacuum is not dead but is whispering the creation and annihilation of everything we cannot see. Right at the seemingly immobile foundation of the universe, a hidden, chaotic world is at work, where pairs of particles and antiparticles are constantly being created and annihilated, weaving a grand narrative about the true nature of existence. 1. Quantum vacuum, when emptiness is not truly empty. If you have ever imagined a vacuum as a place completely devoid of matter or energy, it's time to break that notion and step into the strange world of quantum physics. In the classical view, a vacuum is the absolute absence of matter, a perfectly empty space where there are no particles, no electromagnetic waves, and no form of energy whatsoever. While this image is simple and intuitive, it fails to capture the deeper nature of reality as seen through the lens of quantum mechanics. As scientists delve deeper into the fundamental structure of the universe, they realize that a vacuum is far from being just empty space. Instead, it is a vibrant region, filled with incessant fluctuations. The quantum vacuum refers to a fundamental state in which, even when no particles of matter are present, fluctuations of energy persist. This phenomenon is a direct consequence of the Heisenberg uncertainty principle, which states that it is impossible to simultaneously know both the exact position and momentum of a particle. Therefore, even in the lowest energy state, quantum fields continue to fluctuate. Space may appear calm and empty when observed at the macroscopic scale. However, when we zoom down to extremely small scales, close to or smaller than the size of an atom, reality reveals itself to be entirely different. Quantum fluctuations are constantly occurring, creating and annihilating pairs of particles and antiparticles in fleeting moments. They emerge from what seems to be nothing and then vanish back into it. This phenomenon is not merely theoretical, it has been experimentally confirmed and produces measurable effects, such as the Casimir effect. One way to visualize the quantum vacuum is to imagine a calm lake surface. From a distance, the lake appears perfectly still. But as you move closer, you notice tiny ripples continuously dancing across the surface. Similarly, the quantum vacuum, at the smallest scales, is never truly still but is alive with invisible oscillations. What makes the concept of the quantum vacuum so challenging to human intuition is how it redefines our understanding of energy and matter. In this view, energy is not only present when matter exists. Instead, energy exists even in the most fundamental state of space itself. This reality leads to profound consequences in modern physics, including our understanding of the origin of the universe, the formation of elementary particles, and the very nature of spacetime. One of the most famous pieces of evidence for the non-emptiness of the quantum vacuum is the Casimir effect. When two thin metal plates are placed parallel to each other in a vacuum and separated by a tiny distance, they are drawn together without any physical force acting between them. This attraction does not result from gravity, electromagnetism, or any classical force, but from the difference in quantum vacuum pressure between the inside and the outside of the two plates. Only quantum waves with certain wavelengths can exist between the plates, while outside, waves of all wavelengths are allowed. This creates a pressure difference that results in the Casimir force. The quantum vacuum is also deeply connected to the nature of dark energy, which makes up more than 68% of the universe's total energy but remains one of the greatest mysteries in science. Some hypotheses suggest that dark energy could be a direct consequence of vacuum energy accumulating on a cosmic scale. If this is correct, then the seemingly meaningless fluctuations in empty space could actually be governing the fate of the entire universe. The quantum world is a realm where human intuition easily falters. In quantum physics, the vacuum is not simply a backdrop for other physical phenomena to occur upon, it is an active participant in physical processes. Phenomena like Hawking radiation, the Lamb shift, and the Casimir effect could not exist without quantum vacuum fluctuations. Hawking radiation, proposed by physicist Stephen Hawking, is a prime example of how quantum vacuum can have astonishing macroscopic effects. According to this theory, near the event horizon of a black hole, particle-antiparticle pairs are created from the vacuum. One particle falls into the black hole while the other escapes, forming a weak radiation. This process causes the black hole to lose mass over time and, eventually, evaporate completely. The existence of quantum fluctuations in the vacuum also forces scientists to rethink the notion of minimum energy. From the quantum perspective, there is never an absolute zero energy state. There are always fundamental fluctuations, even if they are so small that they cannot be observed directly by conventional means. From our understanding of the quantum vacuum, concepts in particle physics, cosmology, and even future technologies such as quantum computing have been shaped. Empty space becomes a natural laboratory for discoveries about the deepest nature of reality. But why do these fluctuations exist even in what is supposed to be the most minimal state of space? At first glance, this seems to violate our intuition about the conservation of energy. However, in quantum mechanics, the principle of energy conservation holds strictly only over long periods of time. Over extremely short intervals, the uncertainty principle allows for temporary, slight deviations. The particle-antiparticle pairs that emerge from the vacuum are the physical manifestation of these deviations. They exist for an exceedingly brief moment and then annihilate each other, returning the borrowed energy to the vacuum. It is fascinating to think that the entire universe, with all its stars, planets, and life, may have begun as a tiny quantum fluctuation in a primordial vacuum state. Many modern cosmological models, including the theory of cosmic inflation, are based on the assumption that the universe originated from a quantum instability in the vacuum. The fact that the vacuum is not truly empty also raises profound philosophical questions about the nature of existence. If what we call nothingness is actually filled with infinite potential, does true nothingness even exist? Or is nothingness merely an expression of the limits of human perception of unseen, underlying activity? Today, theoretical and experimental physicists continue to explore the properties of the quantum vacuum. Experiments using particle accelerators such as the LHC at CERN are helping to test the predictions of quantum field theory. Technologies like quantum sensors and quantum computers also harness quantum fluctuations in the vacuum for practical purposes. The quantum vacuum is not just a remote theoretical concept. Insights from it are being gradually applied in practice, promising to bring about major breakthroughs in science and technology. From developing ultra-precise measurement systems to discovering new states of matter, the quantum vacuum is opening doors to realms humanity has never seen before. The quantum vacuum stands as proof of the astonishing richness of nature. Even in a state that seems utterly empty, the universe teems with invisible but powerful activity. This concept forces us to view the world with entirely new eyes, where even emptiness itself is filled with wonder. Empty space is not the death of everything but the secret cradle where infinite possibilities await discovery. In the quantum view, the vacuum is both the beginning and potentially the end of every story about this universe. 2. Quantum effects in vacuum, the oscillations of an invisible reality. If reality can be likened to a grand stage, then the quantum vacuum is the ever-shimmering backdrop, where the most wondrous events quietly unfold without our awareness. We have discovered that vacuum, from the quantum perspective, is not empty at all. It is a seething region of space, teeming with microscopic activity. Building on this fundamental truth, we now delve deeper into the nature of what is known as quantum effects in the vacuum, where random but ceaseless fluctuations paint the background of the entire universe. Quantum effects in vacuum describe one of the most fundamental and indispensable phenomena of nature. Even when no real particles, no light, and no electromagnetic fields are present, the vacuum is never completely still. At the quantum level, energy fields continuously undergo random fluctuations, generating tiny energy pulses, with pairs of particles and antiparticles spontaneously appearing and disappearing in unimaginably brief moments. Why does this phenomenon occur? The answer lies in Heisenberg's uncertainty principle, one of the pillars of quantum mechanics. This principle asserts that it is impossible to simultaneously determine both the energy and the time of a system with perfect precision. Therefore, over extremely short periods, the system's energy can fluctuate freely. These fluctuations are the very quantum fluctuations of the vacuum. Imagine an endless ocean. Although its surface may appear calm, beneath it lie countless undercurrents and tiny whirlpools in constant motion. The quantum vacuum is much the same. Every smallest point in space can be thought of as a tiny wave, a vibration of energy in constant play, despite the seemingly tranquil appearance. These quantum fluctuations are not merely an abstract theoretical concept. They have practical consequences and can be measured. One of the most famous results is the Casimir effect, which we have previously discussed. Yet the Casimir effect is just the tip of the iceberg. Quantum fluctuations profoundly impact the stability of atoms, the existence of interatomic forces, and even influence the evolution of the universe during its earliest moments. More specifically, quantum fluctuations in vacuum arise from the incessant oscillations of quantum fields such as the electromagnetic field, the Higgs field, and many others. Each of these fields can generate their corresponding particles. For example, the electromagnetic field can produce photons. In the vacuum, even though there are no real photons traversing space, fluctuations in the electromagnetic field persist, generating virtual photons that exist for extremely fleeting moments. These virtual particles are the ephemeral products of energy fluctuations. They appear in pairs, a particle and an antiparticle, borrowing energy from the vacuum and existing only for a moment before annihilating each other and returning the borrowed energy. From the quantum point of view, these virtual particles do have real effects on their surroundings, even though they cannot be directly observed with conventional instruments. One place where this phenomenon becomes most evident is in the case of Hawking radiation near the event horizon of a black hole. Quantum fluctuations near the black hole's edge can cause a particle-antiparticle pair to separate, with one falling into the black hole and the other escaping. This process leads to the gradual loss of mass from the black hole over time, a concept that revolutionized our understanding of black hole physics. Quantum effects in the vacuum also play a crucial role in the theory of cosmic inflation. In the first moments after the Big Bang, tiny quantum fluctuations in energy density were stretched to cosmic scales by the rapid inflation of space. These fluctuations later became the seeds for the formation of galaxies and large-scale structures of the universe. Not only do they affect macroscopic physics, but quantum effects in the vacuum also have direct consequences at the atomic and molecular levels. For instance, the Lamb shift, a slight but measurable shift in the energy levels of the hydrogen atom, is the result of interactions between the electron and the vacuum quantum fluctuations. The discovery of the Lamb shift marked a major milestone in confirming the physical reality of vacuum fluctuations. In recent years, with the development of ultra-cold technology and ultra-sensitive measurement techniques, scientists have begun to harness quantum effects in the vacuum to develop quantum sensing devices, enabling the measurement of incredibly small changes in gravitational or magnetic fields. These devices may usher in a new era of astronomical observation, gravitational wave detection, or even the discovery of signals from hidden spatial dimensions. Another striking example of the tangible presence of quantum fluctuations in the vacuum is the emergence of nonlinear effects in quantum optics, where light interacts with light through the background fluctuations of the vacuum. Normally, in classical optics, light passes through light unaffected, but in extreme quantum environments, these interactions can occur, opening doors to unconventional optical technologies. Going even deeper, it has been proposed that the very properties of space and time might emerge from underlying quantum fluctuations. Some theoretical physicists are exploring the possibility that spacetime is not a fixed backdrop but a phenomenon arising from extremely microscopic quantum relationships. From this perspective, the existence of space and time as we know it could be merely a consequence of countless complex quantum fluctuations. An interesting fact is that these quantum fluctuations cannot be eliminated. Even if a system is cooled to near absolute zero, quantum fluctuations still remain. This is why the quantum ground energy, or vacuum energy, is never zero. This reality has major implications. For example, in efforts to create stable quantum computers or devices that require absolute control over quantum noise. One of the most mysterious aspects of quantum effects in the vacuum is how they can give rise to macroscopic phenomena from minute fluctuations. In inflationary models, a tiny fluctuation in vacuum energy density could eventually lead to the formation of an entire galaxy billions of years later. This illustrates the power and significance of quantum fluctuations right from the dawn of the universe. Far from being mere abstract theories, quantum effects in the vacuum are gradually becoming part of future technology. Techniques such as quantum resonance, quantum information transfer, and quantum sensing all rely on the ability to control and exploit these microscopic quantum oscillations. The ability to measure and control quantum fluctuations in the vacuum also presents major challenges. On the one hand, they offer infinite potential for technological development and scientific discovery. On the other hand, they impose fundamental limits on the precision and reliability of any measurement. No device, no matter how sophisticated, can completely eliminate background quantum noise. The deeper physicists explore quantum effects in the vacuum, the more they realize that these fluctuations are not merely sources of noise but are also the origin of all innovation. The quantum vacuum, with all its random yet non-chaotic oscillations, is the launching pad for the formation of matter, energy, and perhaps even consciousness itself. Looking back at the journey from an apparently empty vacuum to a ceaselessly vibrant foundation, we can understand that reality is far more intricate than what the naked eye perceives. Every tiny speck of dust, every faint beam of light, every beat of time, all arise from those unseen yet profoundly real oscillations. Quantum effects in the vacuum are not merely academic concepts, they are keys to unlocking new understandings of the nature of reality, sparking the next revolutions in science. As humanity continues to take great strides in exploring the universe and itself, it will be a deeper understanding of the silent oscillations within the quantum vacuum that lights the way forward. 3. The birth of particle-antiparticle pairs, when the vacuum becomes a dance of creation. In the seemingly absolute stillness of space, a place where human reasoning has long assumed to be completely empty, an endless dance between particles and antiparticles takes place, revealing that the nature of existence is far more complex than the limits of imagination. Following the discoveries regarding quantum fluctuations in the vacuum, we now delve into one of the most spectacular manifestations of these foundational disturbances, the temporary creation of particle-antiparticle pairs. From these random energy fluctuations, the quantum vacuum not only oscillates but also gives birth. It allows matter to appear fleetingly before vanishing again, like strange flashes against a motionless backdrop. At a fundamental level, according to quantum mechanics and quantum field theory, random fluctuations in the background energy can give rise to particle-antiparticle pairs, with each pair consisting of a particle bearing specific physical properties and its antiparticle carrying opposite attributes. For example, if a particle has a negative electric charge, its antiparticle will have a positive charge. If a particle has upward spin, its antiparticle will have downward spin. The creation of particle-antiparticle pairs can be visualized as tiny ripples bursting forth from the quantum ocean. For extremely brief moments, pairs are born, exist fleetingly, and then annihilate each other, returning the borrowed energy to the vacuum. This process does not violate conservation laws because the lifetime of the particle-antiparticle pair is strictly constrained by the Heisenberg uncertainty principle between energy and time. The basic formula from the uncertainty principle, where E is the energy uncertainty, T is the time uncertainty, and is the reduced Planck constant, allows small energy fluctuations over extremely short timescales to create matter without violating the overarching rules of nature. The creation and annihilation of particle-antiparticle pairs occur everywhere, at every moment, throughout the entire universe. This is not merely a play of empty space but happens even in extremely high-energy environments such as near black hole surfaces, during the Big Bang, or in modern particle accelerator experiments. More specifically, when a sufficiently strong energy fluctuation occurs in the vacuum, that energy can transform into a particle and an antiparticle pair. If the two do not immediately meet and annihilate, they can be observed as real physical entities. This opens up the possibility that even all the matter we know today, from fundamental particles to giant stars, might have originated from such primordial quantum events. A notable example of particle-antiparticle pair creation in natural conditions is Hawking radiation. Near the event horizon of a black hole, particle-antiparticle pairs can be created. One particle falls into the black hole while the other escapes, forming a radiation stream. This process causes the black hole to gradually lose mass over time. Hawking radiation is not just theoretical, it represents one of the most profound predictions merging quantum mechanics and general relativity. In modern laboratory experiments, physicists have sought to create and detect particle-antiparticle pairs. Particle accelerators like the Large Hadron Collider, LHC, at CERN generate collisions at extremely high energies, sufficient to create new particle pairs. When two protons collide at near light speed, the concentrated energy can convert into new particles, allowing scientists to probe deeper into the structure of matter. An important point to emphasize is that during the pair creation process, overall conservation laws are maintained. The energy before and after the pair creation must be equal. Quantum properties such as electric charge, spin, and other quantum numbers must also strictly adhere to conservation laws. This ensures that although matter can arise seemingly from nothing, it never breaks the foundational principles of physics. An intriguing question arises: why, after the Big Bang, does the universe contain more matter than antimatter if particle-antiparticle pairs are always born symmetrically? This is the matter-antimatter asymmetry problem, one of the greatest puzzles in modern physics. Theoretically, if everything were created perfectly symmetrically, particles and antiparticles would have annihilated completely, leaving behind an empty universe. However, reality shows a very small excess of matter compared to energy, and from that tiny excess, the entire material universe formed. Several hypotheses, such as charge parity, CP, violation, have been proposed to explain this asymmetry. Understanding the origins and mechanisms behind CP violation could open the door to deeper insights into the evolution and structure of the universe. Returning to the mechanism of pair creation in the quantum vacuum, it is important to note that particle-antiparticle pairs are not limited to electrons and positrons, the most intuitive example. Depending on the energy levels of fluctuations and the specific quantum fields involved, various types of particles can be created, such as quark-antiquark pairs, virtual photons, or even heavier particles under suitable conditions. Another fascinating way particle-antiparticle pairs can arise is through a phenomenon called Unruh radiation. According to this theory, an accelerating observer perceives the vacuum as a thermal field where particle-antiparticle pairs continuously appear. While Unruh radiation has yet to be experimentally observed due to the need for extremely high accelerations, the theory continues to reinforce our understanding that the quantum vacuum is never truly empty. The creation of particle-antiparticle pairs is not confined to natural cosmic events or large-scale experiments. It underpins a range of microscopic phenomena that directly affect the world around us, from maintaining atomic stability, influencing material durability, to participating in nonlinear quantum optical effects in modern technologies. Researchers are also exploring the possibility of using the process of particle-antiparticle creation for developing new energy sources. Some ideas about harvesting quantum vacuum energy, though still far-fetched technologically, serve as a powerful inspiration for future technologies far beyond today's imagination. In the realm of science fiction, there has long been a dream of utilizing vacuum energy as a clean, limitless energy source. If humanity could one day fully understand and effectively harness the process of particle-antiparticle creation, it could usher in a new era of energy, surpassing traditional limits of fossil fuels or nuclear power. A crucial point to highlight is that although the pair creation process appears random and spontaneous, it is still governed by profound laws of nature. Particle-antiparticle pairs cannot arise chaotically or arbitrarily, they must conform to the structure of the underlying quantum fields and local quantum conditions. Looking deeper into the quantum nature of particle-antiparticle pairs, we uncover the wondrous connection between matter and energy, space and time, between the visible reality and the deep, invisible layers that science is only beginning to glimpse. The continuous creation and annihilation of particle-antiparticle pairs remind us that reality is always in motion, always creative, even within what seems to be the stillest background. Reality is not just a sum of visible things but is also the result of countless invisible events happening beyond the threshold of ordinary perception. Each particle-antiparticle pair flares up and fades like microscopic lightning flashes within the quantum ocean, yet these tiny flashes have helped build the universe. From these fleeting quantum moments, the history of every galaxy, every star, and ultimately life itself, has been written in ink invisible to the naked eye. As humanity continues to delve deeper into the quantum world, our understanding of the process of particle-antiparticle pair creation will not only lead to breakthroughs in fundamental physics but may also pave the way for new technologies and new ways of thinking, bringing us closer to the ultimate secrets of the cosmos. 4. The process of annihilation and temporary existence, a fragile dance between birth and death. In the quantum world, where matter and energy intertwine like a marvelous symphony, existence is never permanent but always a fleeting moment, like a flash of light that flares and then fades into the invisible. Continuing our journey of understanding the creation of particle-antiparticle pairs from the quantum vacuum, we now enter the domain of endings, where every act of creation carries within it the seed of its own destruction, and where every particle-antiparticle pair, after being born, swiftly seeks each other out and annihilates, returning the vacuum to its original stillness. To explain why particle-antiparticle pairs exist only for an extremely short time before annihilating each other, one must first understand the intrinsic nature of this phenomenon. In the quantum field, pair production is not the formation of independent objects but a brief eruption of energy into two opposing forms of matter. This means that particle-antiparticle pairs exist in an extremely fragile state, bound by the most fundamental laws of nature. Heisenberg's uncertainty principle once again plays a central role. According to this principle, on extremely small scales, the precision in measuring energy and time cannot both be absolute. If the energy fluctuation is very large, the time duration must be extremely short, and vice versa. Particle-antiparticle pairs emerging from the quantum vacuum borrow a small amount of energy from the fabric of the universe, but this loan must be repaid almost immediately to avoid destabilizing the structure of spacetime. The lifetime of these particle-antiparticle pairs is determined by the amount of energy required to create them. For example, to create an electron-positron pair, a minimum energy equivalent to twice the rest mass of the electron multiplied by the square of the speed of light is needed. When their existence exceeds the limit permitted by quantum uncertainty, annihilation occurs to ensure the global conservation of energy. The annihilation process between a particle and its antiparticle is not simply their disappearance. When they meet, their combined energy is not lost but released in the form of electromagnetic radiation, typically photons with an energy equivalent to the total mass of the original particle-antiparticle pair. This perfectly reflects the law of energy conservation and reveals the constant transformation between matter and energy at the microscopic scale. In this context, annihilation is not a failure or a tragic end, but rather a reintegration into the foundation of the universe. Particle-antiparticle pairs are like bubbles in the quantum ocean, briefly surfacing before bursting and restoring the primordial calm of the vacuum. Another important factor that hastens the annihilation process is the quantum gravitational and electromagnetic interactions between the particle and its antiparticle. They attract each other strongly and naturally seek each other out to annihilate. Due to their opposite electric charges and opposing quantum properties, annihilation becomes an inevitable outcome, occurring within extraordinarily short timescales, often much smaller than the Planck time, the smallest meaningful unit of time in the universe. In some special cases, if the particle and antiparticle do not immediately annihilate, they can form temporarily bound states, such as positronium, a pseudoatom consisting of an electron and a positron orbiting each other before ultimately annihilating into photons. Nonetheless, the lifetime of such systems is also extremely brief, typically lasting only a few billionths of a second. The annihilation phenomenon is vividly demonstrated in laboratory experiments. Physicists have observed the creation and annihilation of electron-positron pairs in high-energy collisions. When a photon with sufficient energy interacts with a strong electromagnetic field, it can decay into an electron and a positron pair. Later, if these two particles meet again, they annihilate into two photons with specific wavelengths. Beyond the microscopic world, the idea of annihilation is also relevant to large-scale cosmological phenomena. Models of black hole evaporation through Hawking radiation also involve the creation of particle-antiparticle pairs at the event horizon. When one particle falls into the black hole and the other escapes, the black hole loses a small amount of energy. Yet even in this case, the essence of annihilation still dominates the process. The balance between existence and disappearance tightly interweaves all phenomena. Another profound question arises: is it possible to prevent annihilation and preserve particle-antiparticle pairs for longer durations? Theoretically, under extremely special environments, such as near hypothetical white holes or within the conditions of the early universe, annihilation might be delayed or altered. However, under the current natural conditions, the balance between birth and death in the quantum world remains absolute and unwavering. From a philosophical perspective, the process of creation followed by annihilation of particle-antiparticle pairs reflects the impermanence of all existence. Nothing in the universe is permanent, even at the most fundamental level. Every structure, every system, every form of life carries within it the destiny of self-destruction after a certain time, whether as brief as the lifespan of a quantum pair or as prolonged as the lifetime of a galaxy. Another key point is that although particle-antiparticle pairs annihilate very quickly, the total energy and momentum of the system remain perfectly conserved. This shows that in the quantum world, death is never a loss but a transformation of form. Matter returns to energy, and under suitable conditions, energy can once again become matter. Currently, research into particle-antiparticle annihilation is not limited to theoretical physics but has also expanded into potential applications. One promising direction is positron technology, which utilizes antiparticle electrons in nuclear medicine, such as in positron emission tomography, PET, to create detailed images of living tissues. Here, the annihilation process between positrons and electrons is harnessed to detect gamma photons, providing precise information about biological structures and functions. Furthermore, deeper study of the annihilation mechanism opens possibilities for testing theories beyond the standard model. Any small deviation in the annihilation model could point to the existence of new physics, such as undiscovered subatomic particles or previously unobserved weak interactions. As scientists delve deeper into the complexities of annihilation, they have discovered that the process is not completely uniform. Minor variations in initial conditions, surrounding environments, and even in the quantum state of the background field can influence how particle-antiparticle pairs annihilate. These tiny differences can accumulate and lead to microscopic asymmetries, opening the door to advancements in understanding the origins of diversity in the universe. The process of annihilation and the temporary existence of particle-antiparticle pairs is the clearest manifestation of the cosmic dynamic principle, that birth and death, existence and dissolution, are not separate events but endless rhythms of existence itself. From tiny sparks within the vacuum, from fleeting moments of quantum life, the entire universe is woven. Understanding this annihilation mechanism not only deepens our grasp of quantum physics but also our understanding of reality itself, that everything exists in a moment only to serve a greater transformation, a never-ending process where energy, matter, and time are interwoven into an ever-unfinished tapestry. Thus, we have together explored a very small yet deeply mysterious part of the quantum universe, a place where the vacuum is far from silent, but instead brimming with fluctuations and miraculous life. Thank you for accompanying Forbidden Knowledge on this journey. If you have any thoughts, questions, or fascinating theories about the quantum world, don't hesitate to share them in the comments section below this video. Let's discuss and further unravel the mysteries that we have yet to fully understand. Don't forget to subscribe to Forbidden Knowledge and hit the notification bell so you won't miss any of the captivating and mysterious videos we have in store. See you in the next videos. May you always continue to explore and discover unexpected answers within this vast universe.